Hi everyone, and welcome to the Unit 3 review session as we prepare for the final summative assessment from Unit 3. And I'm just going to go over kind of a quick set of study notes that relate all the topics that we covered in this unit, and then I'm going to try to take up the practice assignment that I sent out. So first up, let's just do some quick study notes. We started the unit by doing these conversions, and basically we were learning how to compare, how to use moles as the hub of our analysis. And chemistry likes moles because they're a more relatable, it takes these huge numbers of particles and brings them down to a more relatable amount of things. And so instead of talking about billions and billions of molecules, we can talk about a much smaller 2.3 moles of a substance. And so moles became the hub, and the letter we use for moles is the little letter n. So a little n is the number of moles. The number of particles of a substance is capital N, and the mass of a substance is little m. So those are the main categories that we use. But then we related them. We were able to move back and forth between them. So to move back and forth between the number of moles and the number of particles, we have a relationship. And the relationship is the following. N is equal to capital N over Na. That's how we convert between moles and, or between the number of particles and moles. And then to go back the other way, and what I'll do here actually is that's to go from, if I had the number of particles, so I'm going to get rid of the arrow off of this side. So to go from the number of particles to the moles, what you would do is use that formula, and then to go backwards, to go from moles to the number of particles, you would use this formula. You would say N is equal to N times Na. So that's kind of just a rearrangement of that formula. But so in this case, if you knew the number of particles and wanted to calculate the number of moles, you would use this bottom formula. And if you knew the number of moles and wanted the number of particles, you would use that top formula. And the key is that you always know Na. Na is called Avogadro's number, and it's 6.02 times 10 to the 23. So that's the connection between these. Okay, but we also may want to go from mass to the number of moles. So we may want to go this way. So if we're given mass and we want the number of moles, we have this formula. N is equal to little m over capital M, where in this case, capital M is the molar mass. But we could also do the same thing. We can go the other way using this formula. We can say, well, the mass is equal to little n times big M. And the connection here is capital M, which is your molar mass, and that is obtained by going to the periodic table. So again, you don't have to calculate it. Well, I apologize, you do have to calculate it, but you always can get it by going to the periodic table. So you don't have to be given it in the question. So this is a really important conversion. We spent the first little bit learning how to do these conversions, and then they became very important as we did stoichiometry. So certainly a few questions using those conversions will be on the assignment. One thing I wanted to just quickly identify before we leave it is this definition of particles. Okay, so this capital N, because the definition of a particle can vary a little bit. We have used in the past the term we have used atoms certainly as a particle, but we've also used the term molecule as a particle, and we've used this idea of formula unit as a particle. These are all terms that you will hear in this unit as referring to particles. If you see any of those terms, they're giving you the capital N. But one thing I want to just emphasize is that these two, if the molecule and the formula unit are the same thing. It's just that for molecule, we use the term molecule when we're referring to molecular or covalent compounds. And so I'll just put here covalent, but covalent or molecular. And we use the term formula unit when it's an ionic compound. So for example, a molecule here might be C3H8 is a good example of a molecule. That's covalent. They're both nonmetals. And for a formula unit, it would be something like sodium carbonate. So again, you got a metal and a nonmetal. And so they may ask you for the number of formula units of an ionic compound, but they may ask you for the number of molecules of a covalent compound, but they're the same thing. So just be aware of those different definitions. A kind of a multi-step problem might be to do this. And I'll just give you this one as an example. Calculate, I think this one was on the quiz actually. Calculate the number of atoms in 25 grams of C3H6O3. Okay, so that's a and that would be a 6-mark question. That would be a 6-marker because there's actually a few different steps here. And the reason why that one's so involved is that really what you're doing is you've been given the mass, so you're starting way over here in the mass, and you're going all the way over to calculate the number of particles. So you got to do 2 steps to get there. So look at this. We would first go calculate the number of moles and then calculate the number of particles. And then, but finally, we have one last step as well, because those first 2 steps will tell you how many of the molecules you have, but you also know that you have a total of 12 atoms per molecule. So you'd have to take your final answer and you'd have to multiply it by 12. So I'll quickly do that for you here, just in case people are kind of going, well, I'm getting a little bit confused. So look at this. The first thing I would do is I would calculate the number of moles, which is the sample mass over the molar mass. And so it's 25 grams. There it is. It's the 25. And then I would quickly go to the periodic table and look up the molar mass. So I'd do the molar mass of C3H6O3. And I've already done it, so I'm just going to tell you that it's 90.09 grams per mole. But basically that's 3 times 12.01, 6 times 1.01, and 3 times 16. So that would go there, 90.09 grams per mole. And so when I do that calculation, I get 0.2775 moles. Okay, well, I'm on my way. So now I've gone from here over at the right-hand side to the middle, into the center of the hub. And now what I'd do is I'd go, well, the number of molecules is going to be N times Na. So I would go, well, it's 0.2775 times 6.02 times 10 to the 23. And when I do that calculation, I get 1.67 times 10 to the 23. So at that point, I've calculated the number of molecules that are out there, but I have to still do this last step, is I've got to multiply it by 12 because I know there are 12 atoms in every molecule. And so my final answer is 2.005, or roughly 2 times 10 to the 24 is my final answer. So that's kind of a really good summary question of that first unit. Sorry, the first part of the unit. Okay, the next thing we went into was doing percent composition. So we would look at each element, like so maybe you were interested in the percent of it's the percent of each element in a compound. Okay, so it's the percent of each element in a compound, and the way you get it, in order to get the percent composition, basically what you do is you take the molar mass of the element that you're looking at within the compound, divide it by the molar mass of the compound, and then you multiply by 100. That's how you do it, and I'm going to do a sample question in a moment where we do that. The next thing we did was we calculated empirical formulas, and then as a second lesson, we added in molecular formulas. So notice how I've kind of put it as a little subcategory, because you would always have to first find the empirical formula and then go to find the molecular formula. So what I'm going to write here is that we established that there were 3 steps. So step number 1 of finding the empirical formula was to assume you have 100 grams. Assume you have 100 grams. Step number 2 of the empirical formula is to convert all of the little masses that you just created in step 1, convert mass to moles, and that's using little n is equal to little m over capital M. And then finally, in step 3, you divide by, divide here, let me write, instead of saying, you divide all by the lowest number of moles. Lowest number of moles. Okay, and again, I'm going to show you a little sample of a question in a minute where we do that in the assignment. I'm going to put a little star here, though, is just as a reminder, you can only round if you are within 0.05 of a number. It's a little bit different than normal. Normally we can round, you know, you can when you're doing your significant digits, you can round if, you know, if it was 0.67, you could round up to 0.7. But with these empirical formulas, you've got to be fairly close, and if you're not, you've got to consider multiplying everything by a number. And there's a table in your book that shows you, for instance, if after you've done this division in step 2, you ended up with the following numbers. Let's say you ended up with 1, 2, and 1.33. You can't round that 1.33 down to 1. You may say, well, I want all whole numbers. I don't want any decimals. And you're right. But what you'd have to do is multiply them all by 3, and so you'd end up getting 3, 6, and 4 here. And that would, you know, that's going to be your empirical formula. So just be careful of that last step. And finally, just the only thing, so for molecular formula, you do the same 3 steps, you just add in a 4th step just for the molecular formula. And what you do is you need the multiplier. And to get the multiplier, you do the molar mass of the molecular formula divided by the molar mass of the empirical formula. And this number, this would have had to have been given to you in the question. Given in question. Okay, so just be aware of that. Obviously, the molar mass of the empirical formula you can calculate having done steps 1, 2, and 3. Okay, all right. So the last thing we did in this unit was stoichiometry. And basically, stoichiometry is all about using a balanced equation, using a balanced chemical equation, using a balanced chemical equation to determine determine amounts used or produced in a chemical reaction. So what I'll tell you is that stoichiometry, it's all about recipes. It's all about using a recipe to figure out what you're going to make. And I think this analogy to cooking is a good one. I also used an analogy to manufacturing, with bikes and with cars, but I also used it with chocolate chip cookies. But this whole idea of being able to use these numbers to predict what you're going to make. Okay, now there are 4 steps to stoichiometry. These are very critical, and essentially you've got to move through these steps in these questions. Here they are. Steps involved. So step number 1 is you write the balanced chemical equation. Write the balanced chemical equation, and oftentimes you are given it, which is nice, but you don't have to be. Write the balanced chemical equation. And then I put a little note is write what you are given. Write what you are given. Okay, so make sure that you're done step number 1 when you've written the balanced equation, and then underneath the appropriate compounds you've written what you've been given. Okay, step number 2 of stoichiometry is to convert everything to moles. Convert to moles. Now, sometimes we have 2 ways of converting to moles. We could do a little m over a capital M, or we could do n is equal to capital N over NA. So don't forget that you've got 2 different ways. You could be given the number of particles, or you could be given the sample mass. Step number 2 is always converting to moles. Step number 3 is the critical one. Step number 3 is where you do a mole ratio. So here is where you pick the 2 things that you're interested in. So mole ratio always involves only 2 of the substances. Even though the equation has 4 substances in it, or maybe 5 or 6, it doesn't matter. In this step, you're going to focus in on 2 of the substances. You're going to set up the ratio, and always one part of the ratio will come from the coefficients in the balanced equation. I'll put a star there. One ratio comes from the balanced equation. Okay? But just remember, you focus on the 2 things the 2 things you're going to be doing are one thing that you're given something about and one thing that you need. The last step of stoichiometry is convert back to what's required. Convert back to what is required. So normally, you leave step number 3 with the number of moles, but normally they've asked you to calculate, let's say, the mass. And so you've got to use a formula like this to convert those moles that you calculated in step 3. Sorry, that's a capital M there. To convert the moles back to the mass. Now, there were 2 little extra things that we talked about in stoichiometry, 2 extra lessons. And the first one is limiting reactant. And so I'm going to put a little star here, is that we've got to modify step 2 a little bit. So it means you've got to do a bit more work. You got to modify step 2. Because in this, for a limiting reactant, you're given 2 reactants, and you've got to figure out which one is going to run out. So which one is limiting? Because that's the one you're concerned about. In order to predict how much will be produced, you need to know which one is going to run out. And the way you do that is, first of all, you still do step 2 as normal. So in this case, though, you're going to calculate 2 moles. You'll calculate 2 moles, Okay, so let's say you've calculated N1 equals something and N2 equals something else. Now, you're not done at that point because you may argue, well, whichever one of those is the lowest is the limiting reactant. But you've got to do what I call step 2A here, which is you then have to divide by the coefficient, from the balanced equation. Because that indicates how fast each of these are used up. So and now once you've done that 2A, so look at this, you divide by whatever the coefficient is. I'll call it for this one, little a, and divide this one by little b. And then whatever you get here between these two numbers, those will tell you whichever one of those is the lowest is your limiting reactant. And so I'm just going to put here, divide by the coefficients from the balanced equation. So I'm going to say little a and little b. So let's say your equation had been, little a, capital A, plus little b, capital B, where the little a and little b are the coefficients, and they produce something. So that's what you're dividing by. So just be careful of that. Now, the one other thing I'm going to say is that once you've established which is the limiting reactant, please remember to go back to this value to use in your step 3, or this value, whichever one was limiting. That's what you use in step 3. So you've used this little extra calculation to figure out which one was limiting, but then go back to the number of moles in your step 3. Okay. Finally then, I'll just drag this. The thing we finished off with was percent yield, and the formula for percent yield is equal to, it's the actual yield, so what you actually got from the chemical reaction, divided by the theoretical yield, and theoretical is what stoichiometry predicts, divided by the theoretical times 100. And so we did a few questions involving percentage yield, and maybe knowing the reasons. I'm going to put here, what are some of the reasons why you don't get the theoretical yield? So we talked about that in our note. Okay, here we go. Let's go and try this. Let's go and take up the assignment now. So I'll go to the assignment. All right, so I thought that these were good examples of questions. The quiz, or the assessment, will be divided into like a short online quiz where you'll do some multiple choice questions, and then an assignment that you will do full answers for. So here we go. Let's run through these. So look at this. If you're doing a question like this, it says here, how many molecules of sulfur dioxide? So we know that that's SO2. How many molecules are present in 1.6 moles? Oh, we're given a little n. And so when they're asking for molecules, it's capital N. So I quickly say to myself, well, N is equal to N times Na. So it's going to be 1.6 times 6.02 times 10 to the 23. And when I do that calculation, I get 9.63 times 10 to the 23. Now, there was no trick to this. It just asked me for the molecules. It didn't say the number of atoms, so I don't have to change that. Oh, good. Okay, it's A. Next one says, how many moles are there in, okay, we got a little m for this one, and it's aluminum sulfate. So I'm going to write that over here. It's Al, and then it's SO4, but wait a second, Al, I've got to go, it's a +3 ion, and SO4 is a -2, so I've got to crisscross those. Okay, that was important to do because I know that in order to get the number of moles, I'm going to have to go and get the molar mass. It's little m over capital M. And so I quickly go to my periodic table and I'm going to calculate my capital M of aluminum sulfate. And so I look at each of these, and so it's going to be 2 times the mass of aluminum. Well, I look on the periodic table, and aluminum is 26.98. 26.98 grams per mole plus. Look at this. There are 3 sulfurs. The 3 affects everything in the brackets, so it's 3 times 32.07 plus. And then look at this, 3 times 4, there are 12 oxygens there, so 12 times 16. And so aluminum sulfate weighs 342.17 grams per mole. So it's going to be 87.6 grams divided by 342.17 grams per mole. And when you do that calculation, you get 0.256 moles. Beautiful. Another A. Okay, what is the empirical formula of benzene? Well, there's no calculations really here, other than to know that the empirical formula is the simplest. It's the simplest whole number ratio. So I've got to look at this and say, is that in simplest form? Well, no, it's not. Really, this one, because 6 can be divided evenly by 6 in both cases, the empirical formula is CH. It's the simplest one, so it's C in this case. Okay, number 4, diethyl oxalate is a solvent that is used in perfumes. Its empirical formula is this. Okay, that's cool. So we've got the empirical formula. Right there, and I'll just kind of make a little note for myself. It's the empirical formula. Oh, but they've given me the molecular mass. So look at this. They've given me the capital M of the molecular formula here, 146.14. So what is the molecular formula? Oh, well, this is one of those ones where I've got to do the multiplier. So look at this. I'm quickly going to calculate the molar mass of the empirical formula. So look at this. I'm going to work with this one. And when I do that, it's going to be 3 times 12.01, there's the carbon, plus 5 times 1.01, that's the hydrogen, plus 2 times 16. And when I do all that, I get 73.08. So that's the molar mass of just the empirical formula. And then look at this. We're going to come over here, and we're going to divide. And this is what I showed you in the study notes. You divide those two, and you get a multiplier of 2. So really it means that in order to get the molecular formula, we've got to multiply my empirical formula by 2. Every one of those subscripts gets multiplied by 2. So to be 6, 10, and 4. Oh, there it is. It's D. Okay. I got rid of question number 5 on mine, so this is question number 5. So it says, consider the following balanced equation. I'm going to write it over here. It says 2Na plus Cl2 makes 2NaCl. There it is. If 4.12 moles of chlorine. So look at this. I've been given the number of moles of chlorine. 4.12 moles of chlorine react with sodium metal. How many moles of sodium metal are consumed? Now, this is stoichiometry, but the nice thing about it is it's a really simple stoichiometry question because they've already done step 2 for us. They've already converted it to moles. And so all I need to really do is the mole ratio. So look at this. I pick the 2 things that I'm interested in. So one thing I'm interested in is Na, and the other thing I'm interested in is Cl2, and that's because I've been given something about the Cl2, and I need something about the Na. So we always go to the balanced equation for one of my ratios. So there it is. It's a 2-to-1 ratio. But look at this. I've been given 4.12 here, and I need to solve for how much Na. The way you solve these is by cross multiplying to get the x. And so X is going to be equal to 8.24. That's the number of moles I need. I'm done. That was a really kind of a simple one. We didn't have to do step 2 or step 4 because all they wanted to do, figure out how many moles. And so my answer is B. Okay, let's do a couple more multiple choice here. So this one says, consider the following balanced equation. Oh, this one's going to be a little bit more challenging because it's given me a mass. So calcium plus 2H2O makes CaOH2 plus H2. So you've been given a mass of 1.2 grams here, and it says how many moles of calcium hydroxide. So they want the number of moles of the calcium hydroxide produced. Okay, so that's where we're headed. So I've done step number 1 of stoichiometry. Let's do step number 2, which is convert to moles. So N is going to be equal to little m over capital M. And for the capital M of calcium is pretty easy. I just have to look it up, and it's on the periodic table. It's just 40.08. So here, the moles I got was 0.0299. That's the number of moles. Well, this is kind of an easy one as well, because step number 3 is to do the mole ratio. But you can see here that the ratio of calcium to calcium hydroxide is a 1-to-1 ratio. Look at that. That's a really nice ratio, because if it's 1-to-1, you know that whatever the moles of the one are, it's going to be the same. So X here, in order to make those ratios the same, it's just the same number. So there you go. It's just A. Okay, the last one is a percentage yield. It says the percentage yield is 82%. If the theoretical yield is 950 kilograms, what does the actual yield need to be? Well, let's work with our formula. So percentage yield, whoa, having some difficulties there. Percentage yield is equal to the actual yield divided by the theoretical yield times 100. So in this case, we've got 82% is equal to actual yield over 950 kilograms times 100. So you get the 100 over to the other side by dividing it. So that if you divide the 100 here and divide the 100 here, that turns into 0.82 is equal to the actual yield divided by 950. And then you get rid of the 950 by multiplying both sides. Whatever you do to one side of math, you've got to do to the other. And so it's going to be 0.82 times 950. And when you do that, you get 779 kilograms. Okay, so there's B. All right. We've also got some short answer questions here. So let's go through those. It says, what is the percentage composition of sodium phosphate? Okay. Well, this was one of the first things we did in this unit. We did the percentage of each of the elements. So first of all, let me write sodium phosphate. And I know that because sodium is a +1 and phosphate is a -3, I've got a crisscross. So there we go. That's sodium phosphate. And so here we go. The percentage of sodium is going to be equal to the amount of sodium within this. So it's the mass of the element sodium. So it's going to be 3 times 22.99. I got that from the periodic table, divided by the molar mass of the whole thing. So I'm going to go over here and calculate the molar mass of sodium phosphate. And so here we go. It's 3 times 22.99 plus 1 times 30.97. That's for the phosphorus. And then 4 times 16. That's for the oxygen. And when I add all that up, I get 163.97. So I'll come over here and I'll go 163.97. And then I'll multiply it by 100 to get the percent. And when I do that, I get approximately 42%. Okay, then we'll do it for the percent of oxygen. So we've taken care of the sodium. Now I'll do the oxygen. So it's going to be 4 times 16. So notice that I'm actually just using that portion of it. And then I divide by the 163.97. And when I do that, I get 39%. And then finally, for the percent of phosphorus, it's just there's only one phosphorus, so it's just going to be the 30.97 divided by the 163.97 times 100, and there I get 19%. And I should just, if I've done my rounding correctly, those three should add to the 100%. So just double check it, to make sure it works. Okay, why is the limiting reactant not necessarily the reactant available in the least amount by mass? So what this one is saying is that when you're given two reactants, a grade 9 might look at it and say, well, the one, if you were given 10 grams of one and 5 grams of the other, the 5 grams will be limiting. But you need to explain to him why that's not always the case. Like in some cases, the 10 grams actually may be the limiting. And so here's my answer. I would say to that one, substances can weigh different amounts. Substances can weigh different amounts. So you first have to convert mass to moles. To compare the count. So we've got it. We can only compare counts to compare counts. So that's the first thing. Also, you have to consider the coefficient. You have to consider the coefficients because substances, or I'll say because reactants are used at different rates. Reactants are used at different rates. In other words, if it has a bigger coefficient, it's used up faster, and so you need to account for that. Okay. Use an analogy to explain the concept of percentage yield in stoichiometry. So I used analogies all over the place, but I certainly used it to explain percentage yield, and the one I used was baking cookies. So the analogy, I would certainly use my analogy, baking cookies. The recipe says you will get 24 cookies, but you only get let's say you get 22 cookies. So that works out to a 92% yield. So that's there you go. That's the example. Some cookie batter is eaten by your little brother or little sister, and also cookies are different sizes. You don't make them all identical, and maybe you made some of them too big, and so that's why you didn't get the amount. So that's you're just using this analogy to explain something from chemistry. Okay, here we go. Here are some other ones. This one's an empirical formula question. So it says, let's use those steps that we decided. So step number 1 is assume that you have 100 grams. So that way, for the potassium, we would have the mass would be 38.67 grams. If that's the percent, and if you only had 100 grams, it means that you'd have that number of grams. Okay, for the nitrogen, we would have the little m would be 13.85 grams, and for the oxygen, the little m would be 47.48 grams. Okay, step number 2, calculate the number of moles. So little n is equal to little m over capital M. And so in this case, it's 38.67 divided by 39.10. And when I do that, I get 0.989 moles. Here, it's going to be 13.85 divided by 14.01. And I get 0.988 moles. And here, it's 40. Oops. Oh boy. It's 47. 40. Oh boy. 47.48 divided by 16. And here you get 2.97 moles. Okay. Step number 3 of these empirical formula questions is divide by the lowest number. So look at this. This is my lowest. So I'm going to go 0.989 divided by 0.988. And when I do that, I get approximately 1. I'm going to do 0.988 divided by 0.988, and I get exactly 1. And then I'm going to do 2.97 divided by 0.988, and I get approximately 3. They're all within 0.05 of those numbers, so I don't have to multiply anything. And so my final empirical formula is K1N1O3. There's my empirical formula. Okay, here we go. We're going to get into a stoichiometry question. It says, one reaction that is used in the smelting of involves copper 1 oxide and copper 1 sulfide. These two compounds react to produce copper and sulfur dioxide. So in this case, you're not given the balanced equation, so you've got to come up with it. So here we go. I need to write my formulas. So I've got copper, and then it's a +1, that's what the 1 means, oxide. Now oxygen is always -2, so copper 1 oxide is C2O. Okay, I'm done with my charges. Plus, I've got copper 1 sulfide, so that's Cu +1. Sulfur is always -2, so there it is, Cu2S. React together to make copper. Well, copper can exist on its own, so it's just Cu plus sulfur dioxide, so it's SO2. Okay, let's balance it. So I quickly look at this, and I'm going to say, well, I need 2 oxygens over here, so I'm going to put a 2 out front here, and then that gives me 6 of the coppers, so I better put a 6 there. Oftentimes the balancing is pretty easy like that, so I'll just write it like that. So there's my balanced equation. Okay, and then it says 86 grams of copper 1 oxide. So look at this. I'm given a mass here of 86 grams. Reacts with 46 grams, so a mass here of 46 grams. Determine the mass of copper that is produced. Okay, so here we go. The mass is a question mark. You guys, we've done step number 1 of stoichiometry. We've written the balanced equation, and we've written what we've been given. Okay, so here we go. My step number 2 is to convert to moles. So here we go. N is equal to 86, and I've got to go calculate my molar mass of copper 1 oxide, and I've already done that, so it's 143.1, and so when I do that, I get 0.601. Got to go do the same thing with my copper 2 sulfide. So the number of moles there is 46. And the molar mass of the copper 1 sulfide is 159.17. So the number of moles I get there is 0.289 moles. So there you go, I've done that. Well, which one of them is limiting? So what I've got to do, I've got to do that little step 2a here. So watch what I'm going to do. I'm going to do 0.601 divided by 2. And over here, I'm going to do 0.289 divided by 1. And when I do that, I get 0.3005. So here I get obviously 0.289 whenever divide. So I got to compare these. And so when I compare them, this one is the lowest. So that's the one that's limiting. So oftentimes what I do is I even cross this one out just lightly, just to remind myself that it is the excess reactant. I don't have to worry about it. This is the one I'm concerned about. Okay, so let's go on to step number 3. So step 3 of stoichiometry is to do a mole ratio. So clearly I've got to pick 2 of these. I've got 4 things to pick from. I got to pick 2 of them. Well, I'm interested in this one and I'm interested in this one. This is the one that I got to solve something for, and this one is the limiting reactant. So here we go. I go Cu2S compared to Cu. I always get one ratio from my balanced equation. So it's a 1 to 6 ratio. 1 to 6 ratio. But look at this. I actually, and remember, I go back to this one. Now, it just happens to be the same number, but it's 0.289 to x. I cross multiply, and so the number of moles I get there is 6 times 0.289. 6 times 0.289, I get 1.734 moles there. That's the number of moles that I now take up to step number 4. Here it is. Step number 4 is convert back. So mass is equal to N times big M. So it's 1.734 times the molar mass of copper, which is 63.55. And when I do that, I get 110 grams. 110 grams. Okay. So that is how you get move through the steps of stoichiometry. B says if 98 grams is recovered, so that's the actual yield. So look at this. For B, it's just a little short one. It says, what's the percentage yield? So here's B. The percent yield is equal to the actual yield divided by the theoretical yield times 100. So it's going to be 98 divided by 110 times 100. And when you do that, you get an 89% yield, roughly. Okay. Last question. Last question. It says, and I got rid of part C. I think it's not even on yours, so don't worry about it. It says 8.93 grams of lead 2 nitrate is mixed in solution with 1.05 grams of sodium chloride. A double displacement reaction occurs. Okay, so this is again one that you've got to do some formulas. So here we go. Let's get it going. This is kind of unit 2 stuff. So lead 2, so it's +2. Nitrate is NO3. Something is going on there. I don't know what's happening with my pen. Is mixed with, so plus sodium chloride is NaCl. Sorry, I forgot to crisscross here. This is a -1, so I need to crisscross those. So I go bracket, bracket, and 2. So there's lead nitrate, there's sodium chloride. Now it tells me a double displacement occurs, so that's cool. So right away, I know that sodium and I know that Na and NO3 go together. They change partners. and lead and chlorine go together, but I know that that's +2 and -1, and so it's PbCl2. Okay, let's balance it. And so when I balance it, I would need a, well, there's 2 NO3, so I'm going to need a 2 there, and then I'm going to need a 2 there. Like I say, most of these ones are fairly straightforward. Okay, so the mass I've been given here is 8.93 grams. The mass I've been given here is 1.05 grams. And it says, name the excess reactant. So for the first one, actually for A, all I've got to do is really step 2 and step 2A, and then I'm done. But I can see that it says calculate the mass of the excess reactant that will remain. Oh, this is cool. Okay, so let's do this in order. So watch this. For step number 2, let's figure out the excess reactant. That's worth 6 marks. So, okay. So here we go. I'm going to convert to moles. So N is equal to 8.93 divided by the molar mass. Here we go. The molar mass of lead nitrate is 331.22. So you're gonna go into your margin somewhere and go, okay, so here I'll just show you on that one. You'd go down to another page, or I'd like you to show it to me. So you'd go, well, the molar mass of lead nitrate is equal to, and you do, 1 times the mass of lead, 2 times the mass of nitrogen, 3 times the mass, or sorry, 6 times the mass of oxygen. And when you do all that, you get 331. I just don't, I'm already taking a long time in this video, so I'm gonna keep moving here. So you get that, and when you calculate your number of moles there, you get 0.027 moles. Okay, we do the same thing here for the sodium chloride. It's 1.05 divided by the molar mass of sodium chloride, which is 58.44, and you get 0.018 moles. Okay. But now we got to do that step 2A here, because we've got to consider that they get used at different rates. So you take the 0.027 and you divide by 1, because the 1 there, and that's obviously 0.027. And then you take the 0.018 here and divide by 2, and you get 0.009. Okay, so obviously you then compare these two numbers, and this one is smaller. Okay, so therefore the NaCl is limiting. Okay, so I just want to emphasize something here. We go back to this number. We're not going to use the 0.09 anymore. We're going to use the 0.018. Okay, so technically we're done. We're done B, or sorry, we're done A. We've named, oh, it says name the excess reactant. So in this case, the lead nitrate is excess. Okay, so then it says calculate the mass of excess reactant that will remain. Okay, that's kind of cool. So in other words, what I'm going to tell you is that some of this 8.93 is going to be left over. But how much? Well, what I want you to do is let's ignore this. Let's pretend that didn't exist. And let's calculate how much mass will be used if we use up this 0.018 moles of the sodium chloride. Cool. All right, we're ready to go on to step 3 then. So step 3 is do a mole ratio, and look at this. We're going to do a mole ratio of NaCl to the lead nitrate. Those are the two that we're interested in. And so I look from my balanced equation, it's a 2-to-1 ratio. But look at this, I know that I've got the 0.018. That was limiting to X. Now you may say to me, well, Mr. Webster, you know how many moles you have. You have 0.027, but you don't, because now I want to assume that I didn't know how much I had, and I want to know how much was used. So here we go, we're going to cross multiply, and you get 2x is equal to 0.018, and then I got to divide by 2 to get rid of that, so you get 0.009 moles. So that's how much of the lead nitrate. Now, I'm just going to clear this off the bottom just to give myself some room. So the final step, look at this, is to then do step number 4. Oops, I wanted to pick a different color. There we go. Step number 4 is let's convert. So this is how much mole, how many moles of the lead nitrate is going to be used. So the mass that's going to be used is N times big M. So it's 0.009 times the molar mass, which I've already got, 331.22. 331.22, that's the molar mass of lead nitrate. And when I do that, I get 0.009 times 331.22. I get 2.98 grams. Let me just double check that. That looks good. So watch this. So here we go. I'm now finally I'm going to say, well, but if I started with 8.93 grams of the lead nitrate, but I used 2.98, that's what stoichiometry has predicted. So I do 8.93 minus 2.98, and I get, so 5.95 grams is left over. Okay, you guys, so there's the practice assignment. I'm sorry it went for so long. You guys take care and good luck studying.